If you haven't done so yet, please pause the video and try to answer this question first on your own before listening on. In order to understand how to solve this question, what we want to do is draw a picture of a battery first. So the battery would be indicated by this dotted rectangle here, and we can see that it's composed of two parts. We have a source of EMF, or voltage if you will, and then we have this internal resistance right here. In addition, we also have a resistor that has been hooked up to the battery in the form of a very simple circuit. And we were told that that resistance was equal to 72 ohms. So we can actually come in here and mark that as 72 ohms. Also, the EMF of the battery was stated to be 9 volts. So we could put that in as well. And finally, we have a current of 117 milliamps. Make sure you move that decimal place over 3 places to the left so that you can convert it into the standard unit of amps. So that would be the current, and that's been marked in the diagram by the letter I. Now, according to one of Kirchhoff's rules, we can move our way through the circuit in the form of a loop. And while we go through the loop, we're going to keep track of the potential changes. It sounds a bit complex, but we'll begin at this point, and what we'll do is we'll move our way around the circle, around the circuit in this fashion until we return to where we start. Now, beginning at point A, again, we're going to be keeping track of the potential changes. We can see that we move from the negative plate of the battery to the positive plate of the battery. That's going to represent a positive 9-volt potential change. So we can put positive 9 into our equation that we're developing. We then move through the internal resistance, and we recall that for a resistor, the potential change is equal to current times resistance. Now we'll also notice that as we move through this resistor, we will be moving in the direction of the current. Remember, the current is flowing around in this direction. When we move in the same direction as the current, we have a negative potential change. And again, it's equal to the current multiplied by the resistance. So we'll take the current of 0.117 and multiply it by the resistance that we actually don't know. That's what we're looking for in this question. We pass through that internal resistor, and then we come across this resistor over here. Once again, we're moving with the current. And whenever we move with current, we have a negative potential change. It's equal to the current multiplied by the resistance. Now that resistance is known to be 72. Now, once you keep track of all those potential changes, you can set the total potential change equal to 0, and then we're going to be able to solve for R. Why don't we add the 0.117 R over to the left-hand side? We can combine 9 minus the 0.117 times 72. And then we'll divide both sides of the equation by 0.117, and when we do that, we can see that this internal resistance, or lowercase r, is equal to roughly 4.92 ohms. And so this would be the correct answer to the question.